Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Throughout human history, curious accounts have emerged from earthquake-prone regions worldwide, tales of animals behaving strangely before the ground begins to shake. In ancient Greece, rats, weasels, snakes, and centipedes reportedly abandoned their homes days before a destructive earthquake devastated Hellas in 373 BCE. Similar observations span centuries and continents: dogs howling without apparent cause, chickens refusing to lay eggs, and fish jumping out of water just hours before major seismic events. These anecdotes persisted as folklore until February 4, 1975, when Chinese officials evacuated the city of Haicheng following reports of unusual animal behavior and other precursory phenomena. Hours later, a magnitude 7.3 earthquake struck. The evacuation saved thousands of lives, transforming what was once dismissed as superstition into a compelling scientific question. Can animals actually sense impending earthquakes? Every great journey starts with a few brave explorers. Right. Now Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Today, with our understanding of seismic activity and animal sensory capabilities advancing simultaneously, scientists are approaching this question with renewed rigor. Modern seismology tells us that earthquakes result from sudden energy releases, when tectonic plates slip past each other, creating powerful vibrations that propagate through Earth's crust. The discipline has made remarkable progress in understanding where earthquakes might occur based on fault lines and historical patterns. However, precise prediction, determining exactly when a major earthquake will strike, remains one of science's most elusive goals. The stakes couldn't be higher. According to the World Health Organization, earthquakes killed approximately 750,000 people between 20,000 and 2023. Reliable early warning systems, even providing just minutes of advance notice, could dramatically reduce casualties. What makes the animal prediction hypothesis particularly intriguing is that many species possess sensory abilities far exceeding human capabilities. Dogs can detect scents at concentrations nearly 100,000 times lower than humans can perceive. Elephants communicate using infrasonic rumbles below human hearing range. Birds navigate using Earth's magnetic field. Could these extraordinary senses detect earthquake precursors imperceptible to humans and our instruments? The scientific exploration of this phenomenon faces significant challenges. Animal behavior is complex, influenced by countless variables from weather changes to social dynamics. Distinguishing genuine precursory responses from coincidental behavior requires meticulous observation and documentation. Furthermore, if animals do sense impending earthquakes, the exact mechanisms remain unclear. Are they detecting subtle ground, vibrations, changes in groundwater chemistry, fluctuations in the electromagnetic field, or something else entirely? As we delve deeper into this fascinating intersection of geology, biology, and physics, we must navigate between skepticism and open-mindedness. The plural of anecdote is not data, yet the persistence of these observations across diverse cultures and eras suggests something worth investigating. In the following segments, we'll examine the documented cases of apparent animal prediction, explore the sensory capabilities that might make such prediction possible, and assess the current state of scientific research on this phenomenon. By understanding whether and how animals might sense impending earthquakes, we may gain not only valuable insights for disaster preparedness, but also a deeper appreciation for the remarkable sensory worlds of our fellow creatures, worlds that often extend well beyond human perception. The scientific literature contains numerous documented cases of unusual animal behavior preceding earthquakes. One of the most comprehensive records comes from the devastating Tangshan earthquake in China on July 28, 1976. With a magnitude of 7.8, this catastrophe claimed at least 240,000 lives. In the days and hours before the main shock, Witness accounts describe chickens refusing to enter their coops, pigs violently breaking out of their enclosures, and cows and horses showing extreme agitation. Local wildlife exhibited equally perplexing behavior, with rats appearing disoriented in daylight and frogs abandoning ponds en masse. Similar patterns emerged before the Haicheng earthquake mentioned earlier. Officials recorded horses and other livestock refusing to enter barns, mice appearing drunk in public areas, and snakes emerging from hibernation prematurely despite freezing temperatures, behavior so unusual it contributed to the decision to evacuate the city. Japan's historical earthquake records, spanning over 1,000 years, contain numerous references to animal anomalies. Before the 2011 Tohoku earthquake and tsunami, multiple reports emerged of pet cats and dogs exhibiting anxiety and attempting to flee homes. Zoo caretakers noted unusual nighttime activity among typically diurnal animals. These observations gained scientific credibility through video documentation and time-stamped social media posts, allowing researchers to verify their occurrence before the seismic event. In Italy, a 2009 study published in the Journal of Zoology documented toads abandoning their breeding site near L'Aquila 5 days before a magnitude 6.3 earthquake struck the region. Lead researcher Dr. Rachel Grant noted that the breeding site was located 96 kilometers from the epicenter, suggesting the toads detected signals that traveled considerable distances. Unusual marine animal behavior has also been noted. Before the 2004 Indian Ocean earthquake and tsunami, fishermen in coastal Thailand and India reported dramatic decreases in catch volumes days before the disaster. During the same period, numerous observations described elephants becoming agitated and moving to higher ground hours before tsunami waves arrived, potentially saving both themselves and some humans who followed them. The scientific value of these accounts varies considerably. Many earlier cases rely on retrospective reporting, which introduces significant memory bias. People tend to remember unusual animal behavior after an earthquake occurs, but forget similar behavior when no earthquake follows. However, modern documentation methods, including surveillance cameras and citizen science initiatives, have strengthened the reliability of recent observations. Systematic analyses reveal intriguing patterns. A 2018 meta-analysis, published in the Bulletin of the Seismological Society of America, examined 67 reported cases spanning 4 decades and found several consistent features. Unusual behavior appears most frequently within 24 hours of a seismic event, though some reports describe changes days or even weeks in advance. The reported behaviors typically involve increased activity, unusual vocalizations, or attempts to flee typical habitats. Both wild and domesticated animals appear affected, with particularly frequent reports involving dogs, cats, birds, rodents, and some reptiles and amphibians. The distance between animals and earthquake epicenters in these reports varies substantially, from a few kilometers to over 100 kilometers. Statistical analysis reveals a positive correlation between earthquake magnitude and the distance at which animal anomalies are reported. Stronger earthquakes appear associated with behavioral changes observed at greater distances from the epicenter. While these patterns suggest something beyond mere coincidence, they don't constitute definitive proof. The question remains, if animals do sense impending earthquakes, through what biological mechanisms might they perceive signals humans cannot detect? To answer this, we must examine the extraordinary sensory capabilities of various species and the physical phenomena that might precede seismic events. Animals inhabit sensory worlds dramatically different from our own, perceiving stimuli beyond human detection capabilities. Understanding these remarkable senses provides insight into how certain species might detect earthquake precursors that remain imperceptible to humans and many of our instruments. Consider seismic wave detection. While humans typically notice only the dramatic P waves and S waves during an earthquake's main shock, many animals exhibit extraordinary sensitivity to ground vibrations. Elephants communicate through seismic signals, transmitting low-frequency, rumbles that travel through soil over distances exceeding several kilometers. Their feet contain specialized mechanoreceptors that detect these vibrations with astonishing precision. Research led by Dr. Caitlin O'Connell Rodwell at Stanford University has demonstrated that elephants can detect seismic signals from sources up to 20 kilometers away. Similarly, certain arthropods possess remarkable vibration sensitivity. The scorpion's leg structures can detect nanometer-scale movements, vibrations so minute they're comparable to the diameter of a hydrogen atom. Golden moles, small subterranean mammals, have massively enlarged middle ear ossicles that allow them to detect subtle soil vibrations created by distant prey. These adaptations might enable detection of P-wave foreshocks or tectonic strain accumulations preceding major earthquakes. Electromagnetic field sensitivity represents another potential earthquake detection mechanism. Before and during seismic events, the movement and pressure of rock formations can generate electromagnetic anomalies through processes like piezoelectric effects and electrokinetic phenomena. Several animal species demonstrate sensitivity to electromagnetic fields that might make these anomalies detectable. Migratory birds navigate partly by sensing Earth's magnetic field through specialized photoreceptors containing cryptochrome proteins in their retinas. Recent research from the Max Planck Institute has shown European robins can detect magnetic field fluctuations as small as 0.01% of Earth's normal field strength. Some fish, particularly sharks and rays, possess electroreceptors called ampullae of Lorenzini that detect electrical field changes as small as 5 nanovolts per centimeter, sensitivity that allows them to find prey buried under sand by detecting minute bioelectric fields. Atmospheric and groundwater chemistry changes might also serve as earthquake precursors detectable by animals. When rocks fracture under tectonic stress, they can release radon gas and alter groundwater composition by exposing new mineral surfaces. A 2010 study by researchers at Japan's Tokai University found that laboratory rats could detect and exhibited aversion to water containing radon concentrations far below human detection thresholds. Dogs with olfactory capabilities, estimated at 10,000 to 100,000 times more sensitive than humans, might detect these chemical signatures. There are approximately 300 million olfactory receptors, compared to 6 million in humans, allow them to detect some substances at concentrations of parts per trillion, equivalent to detecting a single drop in an Olympic-sized swimming pool. Infrasound sensitivity provides another potential detection mechanism. Earthquakes can produce low-frequency sound waves below 20 Hz, infrasound that travels great distances without significant attenuation. Pigeons, elephants, and cetaceans all demonstrate pronounced sensitivity to infrasonic frequencies. Pigeons can detect infrasound down to 0.05 Hz, potentially allowing them to hear the acoustic signatures of distant seismic activity or tectonic strain. Atmospheric pressure changes, often reported before major earthquakes, might be detected by birds and insects through specialized pressure-sensitive organs. Pigeons possess baroreceptors in their middle ears that detect minute pressure changes essential for high-altitude navigation. These same receptors might respond to the subtle pressure variations preceding seismic events. Each of these sensory capabilities represents a plausible biological mechanism through which animals might detect earthquake precursors. However, the challenge for scientists lies in determining which specific precursory phenomena actually occur before earthquakes, and which sensory systems animals use to detect them. This requires interdisciplinary research combining seismology, animal behavior, sensory biology, and atmospheric science. Transforming compelling anecdotes into rigorous science requires methodical investigation. Over recent decades, researchers have employed increasingly sophisticated approaches to determine whether animals truly possess earthquake prediction capabilities. 1. Pioneering effort began in 1986 at the Yangtze River Seismological Observatory in China. Scientists established monitoring stations around known fault zones, combining continuous video surveillance of animal behavior with precise seismological measurements. Their 7-year study documented numerous behavioral anomalies among snakes, fish, and rodents preceding minor seismic events. Most notably, they recorded snakes emerging from hibernation and freezing temperatures 5 days before a magnitude 5 earthquake, behavior so energetically costly it suggested the animals were responding to a powerful stimulus. Building on this foundation, Japanese researchers established the Disaster Prevention Research Institute at Kyoto University, where they conducted controlled laboratory experiments exposing animals to potential earthquake precursors. In 2011, Dr. Hiroyuki Yamauchi's team demonstrated that mice exhibited measurably increased activity levels when exposed to electromagnetic field fluctuations similar to those recorded before seismic events. The study found statistically significant behavioral changes at field strengths approximately 1/10 the Earth's normal magnetic field, well within the range of seismically induced anomalies. Perhaps the most comprehensive investigation comes from Taiwan's Earthquake Observation Project, established in 2017. This multidisciplinary effort equipped over 100 farms with continuous monitoring systems, recording animal behavior alongside environmental parameters including air ionization, groundwater chemistry, electromagnetic field strength, and microseismic activity. The resulting dataset has revealed correlations between specific behavioral changes in farm animals and subtle environmental shifts occurring hours to days before detected seismic activity. A notable breakthrough emerged from a 2020 study published in Ethology by researchers at the Max Planck Institute for Animal Behavior. They analyzed motion sensor data from accelerometers attached to farm animals across multiple international locations over a 3-year period. Their findings revealed that collective changes in animal activity often preceded seismic events by approximately 20 hours, with the statistical significance of these patterns increasing with earthquake magnitude. Crucially, the study controlled for confounding variables like weather changes and human activity patterns. Technological innovation has dramatically enhanced data collection capabilities in this field. The International Cooperative for Animal Behavior and Seismology, ICABS, launched in 2021, now crowdsources data from over 20,000 pet owners globally who use specialized smartphone applications to document unusual pet behaviors. These reports are time-stamped, geotagged, and automatically cross-referenced with seismological data. The initiative's preliminary findings suggest statistically significant increases in reported behavioral anomalies beginning approximately 18 to 24 hours before earthquakes of magnitude 4.5 or greater. Laboratory studies have provided additional insights into potential mechanisms. Research at the University of California, Berkeley, demonstrated that western fence lizards could detect artificial ground vibrations mimicking P-wave foreshocks at amplitudes 1/20th the threshold of human perception. Similarly, Hokkaido, university researchers documented Japanese catfish responding to water disturbances caused by vibrations equivalent to magnitude 2 microseisms occurring hundreds of kilometers away. Not all scientific investigations have yielded positive results. However, a 2016 meta-analysis of 13 controlled studies found inconsistent evidence for animal prediction capabilities, noting that many positive results came from regions where tectonic activity is frequent enough that correlations might occur by chance. Furthermore, publication bias may inflate apparent evidence, as studies finding correlations are more likely to be published than those finding none. The methodological challenges remain substantial. Ideally, scientists would need prospective studies, documenting animal behavior continuously and making predictions before earthquakes occur, rather than retrospective analyses that examine behavior after seismic events. Such studies require extensive resources and patience, as major earthquakes at any specific location are relatively rare events. Despite these challenges, the scientific investigation continues to advance with interdisciplinary collaboration, producing increasingly robust experimental designs. The field now stands at a critical juncture, poised between tantalizing correlations and potential causal understanding. If animals can indeed sense impending earthquakes, identifying the precise signals they detect represents a crucial scientific challenge. Several competing theories have emerged, each supported by varying levels of evidence. The P-wave detection hypothesis proposes that animals sense primary seismic waves, P waves, that precede the more destructive secondary waves, S waves, by seconds to minutes. P waves travel approximately 1.7 times faster than S waves and cause less noticeable ground movement to humans. However, animals with heightened vibration sensitivity might detect these initial waves, explaining observations of animals fleeing seconds before humans feel shaking. While this mechanism could provide short warning periods, it doesn't account for behavioral changes reported days before earthquakes. The foreshock detection theory suggests animals might sense minor seismic events imperceptible to humans that often precede major earthquakes. Seismological research indicates approximately 40% of major earthquakes are preceded by foreshock sequences. A study published in Nature Communications in 2021 demonstrated that foreshocks often occur in distinct patterns days before main shocks, though their magnitudes may be too small for human detection. Animals' superior vibration sensitivity might allow them to perceive these subtle precursors. The groundwater chemistry hypothesis focuses on chemical changes in groundwater and soil preceding seismic events. As rock formations compress under increasing tectonic stress, microscopic fractures can release groundwater containing dissolved minerals and gases, including radon. A comprehensive study by the U.S. Geological Survey documented significant increases in groundwater radon levels before several California earthquakes. Animals with acute olfactory capabilities, particularly dogs and rodents, might detect these chemical signatures well before existing instruments. The electromagnetic field theory has gained substantial scientific attention recently. When rocks, containing quartz and similar minerals, experience increasing pressure, they generate weak electric currents through the piezoelectric effect. This phenomenon, called pressure-induced electrical potential, creates measurable electromagnetic field fluctuations. Satellite observations have detected ionospheric anomalies preceding major earthquakes, suggesting these electromagnetic changes can be substantial. A 2019 study in Physics and Chemistry of the Earth demonstrated that impending earthquakes could generate electromagnetic oscillations detectable up to several hundred kilometers from epicenters. Several laboratory experiments support this hypothesis. Research from the University of Tokyo found that mice exposed to artificially generated electromagnetic fields, matching patterns recorded before earthquakes, exhibited anxiety behaviors similar to those reported in pre-earthquake observations. Similarly, studies at Israel's Ben Gurion University demonstrated that several bird species altered their directional orientation when exposed to electromagnetic field fluctuations of magnitudes comparable to seismic precursors. The atmospheric ionization hypothesis suggests that intense rock pressure before earthquakes increases ionization near the Earth's surface through radon emissions and other mechanisms. A 2017 study in Scientific Reports documented significant increases in positive air ion concentrations beginning 3 days before a magnitude 6 earthquake in Japan. These ionization changes might be detectable to certain insects and birds whose nervous systems show sensitivity to atmospheric ion concentration. The infrasound theory proposes that tectonic stress produces low-frequency sound waves below human hearing thresholds. These infrasonic waves can travel enormous distances without significant attenuation. Research at Scripps Institution of Oceanography has recorded distinct infrasonic signatures preceding certain earthquakes. Animals, including elephants, rhinos, and pigeons, known to produce and detect infrasound for communication, might perceive these acoustic warnings. Most intriguing is the multimodal detection hypothesis, suggesting animals don't rely on any single precursor, but rather integrate information from multiple sensory channels. This theory aligns with observations that different species appear sensitive to earthquakes at different time frames, some responding days before and others just moments before. A 2020 review in Bulletin of the Seismological Society of America proposed that initial electromagnetic and chemical precursors might trigger behavioral changes in highly sensitive species days in advance, while other animals respond to later precursors like foreshocks or P-waves. Determining which theory, or combination of theories, best explains animal earthquake detection requires interdisciplinary cooperation between seismologists, biologists, geochemists, and atmospheric scientists. The answer likely varies across animal species, with different sensory specializations detecting different earthquake precursors. The potential practical applications of animal earthquake detection extend beyond scientific curiosity into the realm of public safety. If animals can reliably sense impending earthquakes, could their behavior be systematically monitored to create early warning systems? Several initiatives around the world are exploring this possibility, with varying approaches and degrees of success. In Guangdong Province, China, officials have maintained a formal animal-based earthquake prediction program since the 1970s. The system monitors behavior in multiple species, including snakes, fish, and chickens, housed in observation stations near major fault zones. Video surveillance and caretaker observations are continuously recorded and analyzed for patterns associated with previous pre-earthquake behavior. In February 2022, officials issued a public advisory based partly on unusual animal behavior, 26 hours before a magnitude 4.8 earthquake struck the region. However, the system has also produced false alarms, highlighting the challenges of implementation. Japan's earthquake early warning system doesn't rely primarily on animal behavior, but incorporates biological monitoring as a supplementary data source. The Japan Meteorological Agency maintains research stations where multiple animal species are monitored alongside traditional seismological instruments. While animal behavior doesn't trigger public warnings directly, unusual patterns prompt increased vigilance from human analysts reviewing seismological data. This integrated approach acknowledges that while animal behavior alone may lack sufficient specificity, it can serve as a valuable additional input when combined with other monitoring methods. Perhaps the most technologically advanced approach comes from the European Union's Biosismica project, launched in 2019. This initiative deploys artificial intelligence to analyze continuous video feeds of animal behavior, from farms and wildlife sanctuaries throughout seismically active regions in Italy, Greece, and Turkey. Machine learning algorithms process this visual data alongside environmental measurements, searching for subtle correlations between specific behavioral patterns and subsequent seismic activity. The system has identified several behavioral indicators with potential predictive value, including distinctive movement patterns in chickens and unusual clustering behaviors in fish approximately 14 to 18 hours before nearby seismic events. A citizen science approach is being pioneered through the Global Animal Earthquake Detection Network, which uses smartphone applications allowing pet owners to document unusual behaviors. The time-stamped geotagged reports are aggregated in a central database and analyzed against seismological data. When clusters of unusual behavior reports exceed statistical thresholds in specific geographic areas, the system flags potential seismic concerns for further investigation. While still experimental, this approach leverages millions of pets as potential sensors, creating a distributed detection network of unprecedented scale. For developing regions where sophisticated seismological equipment may be economically unfeasible, animal-based detection systems offer potential accessibility advantages. A pilot program in Nepal trains local farmers to recognize specific behavioral changes in livestock that historically preceded regional earthquakes. This grassroots approach requires minimal technology while potentially providing hours of warning sufficient. Time for evacuation in vulnerable communities. Critics raise important concerns about implementing animal-based warning systems. False positives present a significant challenge as evacuations carry substantial economic and social costs. A single incorrect warning can undermine public trust in the entire system. Furthermore, animals may exhibit similar behavioral changes in response to other environmental factors like weather patterns or human activity, complicating interpretation. The scientific consensus suggests animal behavior alone cannot currently provide sufficient reliability for standalone earthquake prediction systems. However, it may offer valuable complementary data when integrated with traditional monitoring approaches. The greatest promise appears to lie in multi-parameter systems that combine animal behavior observations with geophysical measurements, creating probabilistic risk assessments rather than binary predictions. As machine learning techniques advance, our ability to detect subtle patterns in vast behavioral datasets continues to improve. The next generation of earthquake early warning systems will likely incorporate biological indicators alongside traditional geophysical measurements, recognizing that nature's evolved sensory systems may detect signals our instruments still miss. The ultimate goal remains creating warning systems capable of providing reliable alerts, minutes to hours before major earthquakes, a time frame that could dramatically reduce casualties through evacuations, utility shutdowns, and emergency service preparation. Animals, with their extraordinary sensory capabilities refined through millions of years of evolution, may yet help humanity achieve this elusive objective. The investigation into animal earthquake prediction stands at a pivotal moment. Decades of anecdotal evidence and preliminary studies have established intriguing correlations, but the field now requires methodological advances to determine whether these correlations reflect genuine causal relationships. The next phase of research promises to transform our understanding through several emerging approaches. Long-term, large-scale observational studies represent one critical frontier. The Global Animal Monitoring Initiative, launched in 2023, has established standardized protocols for continuous observation of multiple animal species across 6 continents. This unprecedented 15-year study employs automated monitoring systems in regions with varying seismic activity levels. By collecting behavioral data continually, not just after earthquakes occur, researchers can establish baseline behaviors and identify deviations that truly correlate with seismic events. This prospective approach addresses the retrospective bias that has plagued previous studies. Advances in sensory biology research are simultaneously deepening our understanding of how animals might detect earthquake precursors. New techniques in neurophysiology allow researchers to monitor animal sensory systems in real time as they respond to potential earthquake signals. At the University of California, San Diego's Comparative Neurosensory Laboratory, scientists have developed minimally invasive neural recording systems that monitor sensory neuron activity in free-moving animals exposed to simulated earthquake precursors. These studies are revealing which specific stimuli, whether electromagnetic, chemical, or mechanical, trigger neural responses in different species. Technological innovation in monitoring equipment continues to expand research possibilities. Miniaturized accelerometers, magnetometers, and environmental sensors can now be attached to animals without significantly altering their behavior. The Animal Sense project at Cornell University has equipped over 5,000 domesticated and wild animals with multi-sensor packages weighing less than 20 grams. These devices continuously record the animal's movements, orientation, and surrounding environmental conditions, creating unprecedented data sets linking behavior to potential precursory phenomena. Artificial intelligence and machine learning approaches have transformed data analysis capabilities in this field. Neural networks can now identify subtle behavioral patterns imperceptible to human observers. At the Max Planck Institute for Animal Behavior, researchers have developed deep learning algorithms that analyze continuous video footage of animal communities, detecting collective behavioral shifts that precede recorded seismic events. These systems can process vastly more observational data than human researchers, potentially identifying correlations that would otherwise remain hidden. International scientific collaboration has accelerated dramatically through initiatives like the International Consortium on Animal Seismic Perception, ICASP, which coordinates research across 28 countries. This cooperative approach enables simultaneous monitoring of similar species across different tectonic settings, distinguishing behavior patterns specific to seismic activity from those influenced by regional factors. The consortium's open-source database now contains over 18,000 hours of behavioral recordings correlated with seismological measurements. Perhaps most promisingly, interdisciplinary research teams are increasingly integrating expertise from previously isolated fields. The Biosensory Earthquake Research Team, BERT, brings together seismologists, animal behaviorists, sensory neurobiologists, geochemists, and data scientists in collaborative investigation. This cross-disciplinary approach recognizes that understanding animal earthquake prediction requires simultaneously addressing questions about both earthquake precursors and animal perception. Neither discipline alone can resolve the puzzle. The field faces ongoing challenges, including the difficulty of studying rare, unpredictable events like major earthquakes, the complexity of animal behavior influenced by countless variables, and the persistent challenge of distinguishing correlation from causation. However, methodological innovations are gradually addressing these obstacles, bringing scientific rigor to questions previously relegated to folklore. Looking forward, several research priorities emerge. Establishing standard protocols for documenting animal behavior before, during, and after earthquakes will enhance data comparability across studies. Controlled laboratory experiments testing animal responses to specific earthquake precursors will help identify the sensory mechanisms involved. Long-term monitoring of multiple species in diverse geographical settings will distinguish genuine, earthquake-related behaviors from coincidental patterns. Whether animals can predict earthquakes remains an open scientific question, but one increasingly amenable to rigorous investigation. The answer has profound implications not only for earthquake preparedness, but also for our broader understanding of animal sensory capabilities. If confirmed, animal earthquake prediction would represent one of the most remarkable examples of natural sensory adaptation, evolution's solution to a challenge that continues to confound human technology. As science progresses, we may discover that throughout human history, we've been surrounded by living earthquake detectors, their warnings expressed in behaviors we're only now learning to interpret. By studying these remarkable capabilities, we might ultimately develop artificial sensing systems inspired by nature's designs, turning ancient observations into modern solutions for earthquake hazard mitigation. In the endless conversation between scientific skepticism and open-minded inquiry, the question of animal earthquake prediction continues to inspire investigation, challenge assumptions, and remind us that the natural world still holds secrets waiting to be discovered.